This is Mertal and I'm presenting our paper on video captioning for the future frames. The idea for this work comes from the observation that we as humans have the amazing ability to predict what would happen in the near future. For example, if we are seeing a scene of a coach advising a weightlifting athlete, it would be easy for us to determine and predict that later on in the video, the athlete would probably lift the weight again after receiving the advice. We would like to simulate the same thing for an intelligent agent. This problem has a variety of interesting applications in real-world scenarios, such as assistive technologies for people who are visually impaired. For example, we can consider a system that anticipates the possibly dangerous events in the future and tells the users about it in advance so that they can take proper actions. We consider two different setups for this problem. In the first setting that we call the general case, we are given a sequence of frames representing the event that is currently being happened, and the goal is to describe the most likely event that would happen in the next timestamp in the video. However, sometimes, because of the complexity of the scene, the current event can be logically followed by various actions performed by different actors. So, to consider this uncertainty, we introduce the second case that we call the conditional case. In this case, we are given the sequence of frames for the current event as well as the subject for whom we would like to predict the next action. There are three main modules in our proposed method: a temporal feature extractor, a feature predictor, and a captioning module. For the temporal feature extractor, we use an off-the-shelf i3D network that is trained offline and its weights are frozen during the training. It takes V frames for an event and generates a V by D feature map representing the event. TFP module is where we predict the next event. A naive approach would be to directly generate the next event frames. However, because of the scene variation between frames, that would not be an optimal solution. Instead, we use the feature space for prediction and generate the convolution of feature maps for the next event. This module is first trained solely to learn to predict the next event features. To train this module, we feed the features of the current event as well as the length of the next event. A dynamic adaptive pooling layer temporarily shrinks or enlarges the features to match the temporal length of the next event. Finally, with a series of temporal convolution layers, we have the predicted features for the next event. We can now apply L1 loss between the predicted features and the ground truth features of the next event. Now, for the second stage of training, TFP module is inserted into the pipeline and the entire pipeline is trained end to end. We found that in practice, it is always helpful to inject some contextual information into the predicted features. Therefore, we use the current event features as the contextual information and calculate the weighted sum of the features of the current event and the predicted features for the next event. We conduct our experiments on the ActivityNet caption dataset. We also pre-train captioning module on MS Coco dataset in advance. We have a baseline and an oracle to compare with. The baseline uses the features of the current event to generate the caption of the next event, while the oracle solely uses the next event's ground truth features for the caption generation. Our method clearly outperforms the baseline in the general case. In the conditional case also, our method outperforms the baseline. We also empirically find that lambda equal to 0.5 works best for adding the contextual information in both cases. You can find more details about our work in our paper.